In this video, we're going to consider what happens if we take that applied bias and we switch the polarity. And so we're going to call this case 2, or forward bias. So we have our p-n junction here with our built-in electric field across our depletion region. And now we're going to apply a voltage V sub D such that we have a positive polarity on our p side and a negative polarity on our n side. So this is our VD, and we're going to connect it to our p-n junction like this. And so what we're going to see from this is, just like with our reverse bias case, we're going to have an electric field associated with this V sub D. So let me write that in blue. And remember that ultimately our electric field represents the direction that a positive charge would move. So sort of just taking this positive charge, we can say we've got a positive here. Taking this negative sign, we've got a negative here. Assuming we have these ideal wires, it's essentially the same as those polarities of our voltage source. And so what we can see from these blue polarity then, we have an electric field that's going to be going from left to right. So let's call this E sub A, like we did previously, and that's an applied electric field due to our applied voltage. And so what we can see then is that this applied field is opposing our built-in potential. So E sub A opposes our built-in field. And so if we go back and we think about what we talked about with our junction formation, we said initially we have this diffusion process. We have excess electrons over here, so they're diffusing in this direction, so this is diffusion. And we said we have excess holes over here, so these are our holes, these are our electrons. So we had excess holes over here in our P region, which are diffusing over in this direction. So this is what we said initially. But once we had this electric field established based on these exposed charges in our depletion region, we said that that sort of prevents further diffusion. Well, now that we have this applied field E sub A, what it's doing is it's reducing that built-in field, which means that our diffusion process can start up again. So diffusion process, let's just say starts up again. And so what that means is we have electrons going from our N region to the P region. We have holes going from our P region to the N region. And so because we have charge moving, ultimately what that means is we have current flowing. And whether we're looking at holes or electron movement, both of those are going to correspond to the same direction of current, and that's going to be from left to right, and we can call that current, let me put it in a different color so it stands out here, so we can call this current I sub D. Okay, one thing to note, we're not really going to talk about it too much, but because we have our current is dependent on electrons, so once they diffuse we have electrons over here. Because it's based on electron movement over in this P region and it's based on hole movement over in this N region, we can say that this is a minority carrier device. And again, not too crucial to what we're talking about, but just one of those things I think it's useful to at least be aware of. So of course, like with most devices, for instance, the simplest case we can consider is a resistor. We can create we can sort of model a relationship between this current I sub D and this voltage V sub D to get our IV relationships. So let's look at the ideal equation. And so we're not going to go through and derive it. In this case, we're just going to state it, and we're going to see how we can use it and how we can simplify it a little later on in order to make it a little more practical. So our ideal current voltage equation is that current I sub D is equal to I sub S times E to the power of V sub D, so there's our applied voltage, divided by N times V sub T. So V sub T is our thermal voltage, so remember that's about 26 millivolts at room temperature, and then minus 1. So this is what's called our ideal diode equation. So I don't believe we've actually explicitly referred to this as a diode yet, but we'll get into that in the next video. But this is our ideal diode equation. So let me define a couple of these terms that are new. So first of all, the IS is something called our reverse bias saturation current. So remember, when we apply a reverse bias, we said there's no current because that applied field was strengthening our built-in field. In reality, we're going to have a little bit of current leaking through there. And so typical values of this, just to show how small that really is. So typically this is anywhere on the order of 10 to the minus 18 to 10 to the minus 12 amps. So very small current levels. But we do have some current when it's reverse biased. This ID, of course, is going to be much larger because we see that IS is being multiplied by this exponential term. The other new parameter here is this N. We're not really going to deal with it too much in this class, but again, just so you're aware of it, this is our emission coefficient. And so we can kind of think of it as sort of a fudge factor for accounting for what types of processes are going on inside of our PN junction. In most cases, we're just going to assume that N equals 1 unless we're told otherwise. And so we're not going to look at any examples using this equation sort of explicitly, but if you want to get some practice with it, sort of just plugging in, if you're a little rusty using exponentials or anything like that, if you look on page 28, example 1.7, will get you some practice with this equation, as well as get you comfortable with some specific numbers. But again, we're going to talk about some other models and some other things related to this in following videos.